So there are certain statistical assumptions we have to make when we're conducting t-tests, and this is going to go over the assumptions for the one sample t-test, and then we'll continue on with the two sample t-test and the paired samples t-test. So what do we mean by assumptions? So assumptions are the conditions that must be met for the test to be reliable and valid. If the conditions aren't met, then the results of the test may be inaccurate. If the conditions are not met, we usually have to use a different statistical test, or we have to transform our data. And these different tests or the data transformations can correct for violations of the assumptions. So let's look at what the assumptions are. So first off, remember the one sample t-test, we're just comparing a sample mean with a null population for which the mean is known but the standard deviation is unknown. And so here are just a quick list of the assumptions. First off, we assume that the dv is a continuous variable. We assume that the observations are independent, and we have to make the assumption that a simple random sample has been used. We have to assume, assumption 4, that the distribution is approximately normal, and that means that we have, among other things, an absence of outliers. So let's look at each of these individually. So first off, we assume that the dependent variable is continuous. And you'll recall from the start of the semester that a continuous variable is just one where the data points can fall anywhere along a continuum. So like, for example, continuous variables would include things like height. A person could be anywhere within a range of possibilities, 5 foot 4.5 inches or 6 foot 2.2 inches. Scores on a personality inventory, blood pressure, heart rate, distance, number of plants per square meter, and many other variables that are quantitative, as long as each individual could have a score that's different from other individuals along a continuum. So inappropriate variables would be nominal variables. You'll remember that from the start of the term, like favorite color, food preference, sport choices, shoe brands, zip code of residence, etc. Anything that would give a qualitative answer, like a word for an answer, or like zip code of residence, the answer is a number, but it really just represents a category, like a part of the country that you live in. And so all of those would be inappropriate. Also, ordinal variables. So if you had a single item scale, like you asked people to rate their rate on a scale of 1 to 5 your liking for statistics, then each of you would give a 1, 2, 3, 4, or 5 for an answer, and the order would be important. But this might not be appropriate for a statistical test. I wouldn't say that it's never been done, but the closed range of values make it a violation of the assumption of a continuous variable. We do find that scales like this, like the Big 5 personality inventory, you'll notice there were, I think, 44 items on that scale. And those items clustered together so that each person, instead of just one item, 1, 2, 3, 4, 5, their scores would be aggregated or, combined in such a way that this would become a continuous variable because the scores for a number of questions are combined. In any case, you can assume that our data will be okay here. We'll talk about it when you get to your own project. So assumptions 2 and 3 relate to independent observations and the assumption that we have gotten our sample through a simple random selection process. So what do we mean by independent observations? Data for each participant is not influenced by data for any other participant. So appropriate variables, scores for individuals who were drawn individually and randomly from a population. Inappropriate variables, scores for individuals who are systematically related in some way, like not okay, individuals who are selected in related pairs, like pairs of college roommates or pairs of siblings. Then we would have a distortion of the data because those pairs might produce similar scores. Another not okay example would be scores from an oral test where each participant could hear responses of the previous participant, and maybe that would lead them to change their own response. then we also no longer have independent observations. And the assumption that our individuals are drawn randomly from a population, a lot of times we violate that in social sciences, but if we're doing an experiment, it's still okay if we have more than one condition. If we have, like in the independent samples t-test, where people are assigned to one or another condition. So now assumptions 4 and 5, approximate normality and the absence of outliers. So all this means is that the data for the dependent variable must be approximately normally distributed without outliers. And typically, because of the central limit theorem, we've met this assumption if the number in our sample is greater than 30. We looked at some images early in the semester of how even if the population is skewed, the distribution still becomes normal when we reach around 30. We can also assume that we've met this assumption if the population is known to be normal, something like the IQ test or human heights or weights or something. And so when we look at these following histograms, we'll see that all of them are considered normal enough, even though they might not look that normal. And that's because n is greater than 30. And so we can see here, this one has a little bit heavier tables, but it's still considered normal. We can see here there's an outlier, but it's not that severe. We might still consider this to be normal, even though it doesn't look that normal because we've got this n greater than 100. Here we have an n of 30. We can see this one looks pretty normal, and this one looks fairly nicely normal with an n of 100. So this is just to make note that even if they don't look that normal, if we have n greater than 30, they probably still pass the test. Now here we have some examples where n is less than 30, but the population is known to be normal. And so the histogram could appear to be not normal. We can see in the examples coming up that each sample has fewer than 30 participants, and some of them don't look very normal. But because the population distribution is known to be normal, each would still be considered okay. And we can see even this one is on the cusp, but it still makes it when we run the test for it, because we know the population is normal. And these other two with higher n's, these would meet the criteria for normal. So you can't really look at your sample in terms of a histogram and have a super good answer. Then finally, how do we find out if it's normal in the population if it's less than 30 in our sample and the population is not known to be normal, like we don't know about the population? So in this case, we can see that each sample has n less than 30. Some look like they're not normal, but each of these would even still be considered normal enough. We can see this one almost doesn't make it, but we tested it for normality and it does indeed meet the criteria. It's close though. And we can see as n gets bigger, we still have meeting the criteria for normality. We do have some samples here that would not meet the assumption of normality. And so sample A and sample B on the right are both too far off. First off, they have fewer than 30 individuals. Secondly, we don't know if the population is normal or not. And we can see here that these two examples both fail to meet the normality assumption. The outliers are what causes the problem. They're too extreme and they're going to pull that variance up to a much higher level, and they'll be making type 1 error because they'll be detecting the threshold for the tails of the distribution will include more values because of those outliers. So if this is you, what you can do is you want to take a look at your outliers. And you can eliminate them if they're not representative of the population. So for example, maybe you look at the data and you have the survey result and you discover that your participant wasn't paying attention when they were taking your measure or something like that. They were just filling in blanks without really thinking about it. Sometimes you can discern those things. Or maybe you look at it and you find out, oh, all of my sample was pretty similar. They were all between the age of 20 and 30, but this one individual was like 80. And then you could say this person isn't similar to the population, and so they're not really part of the population. Then you could eliminate that individual from your sample. Or maybe you'll look at your data and you'll just discover that you wrote something in wrong. You recorded the data or you gathered the data wrong. You can see that the data don't make any sense. And in that case, you could eliminate it. But you can't just eliminate it if it's inconvenient. If it's inconvenient, but you can't find any reason why this individual would not be part of the sample, then you have to keep them and you have to do a different kind of statistical test. So, testing for normality, there are some ways to do it. First of all, you're going to generate something called a QQ plot. It stands for quantile quantile. And quantile is like, it means just like a percentile. It just tells you what percent of scores, what's the cutoff point for the percent of scores that would be lower and higher than this individual scores. And then with that, we create a scatter plot. I'll give you some examples, of course. And it's the distribution of actual scores, which typically we call observations, the actual scores of your individuals, plotted against what we would expect if the distribution was perfectly normal. And so in a nutshell, how it would be done, you're not actually going to do this process, but what would be done, just so you can make sense of it, is you would rank all the raw scores from smallest to largest. So if you have a bunch of test scores, you would put them in order from the lowest score to the highest score. Then from there, you would determine the predicted quantile, which again is sort of like the percentile. So you could use that percentile calculator tool that we were using, but you'd be doing it for each rank. So you'd be asking in a nutshell, if this was a perfectly normally distributed sample, what percentile would we expect for each score? And what I mean by that is for each rank, for the lowest score in a distribution that's perfectly normally distributed, if there are 20 individuals in that sample, what percentile would we expect the lowest score to be at? So that's how that works. And then we'd go ahead and calculate the raw score for each percentile. We've done that before, the Z2X calculations. And then you'd create the scatter plot using raw scores and predicted scores, and you draw a straight line right through the points. So this is what a QQ plot looks like. And you can imagine that each point represents the lowest actual score compared to the lowest score that would be predicted if it was a normal distribution. Maybe the median actual score compared to what the median would be predicted if it was a normal distribution, and the higher scores compared to what would be predicted for a normal distribution. And so the black line is representing the predicted scores, and the dots are representing your data points, and you want these two to be just like this, as close together as possible, forming a nice straight line, and then you can assume your distribution is normal. If you have some skew, you're going to look at B and C. The tails of the actual scores are going to be diverging from this line, indicating what normal would be. And that means that there's some skew going on in your distribution that's pulling the tails in one direction or in the other direction. So that kind of C shape looking for skew. If, as you see here in D and E, your points are forming sort of an S-shaped distribution, like this one, and like in E, this one, then you can see that you are having a kurtotic distribution where the tails are either really thick or really thin. And we'll look at some images of these again later. And so just in a nutshell, each point in a QQ plot represents the expected scores if the distribution is normal, and the actual scores, and they're called observations. Deviations at the ends of the plot represent skew, and an S-shaped plot, meaning your points are forming an S shape, that indicates kurtosis. Both of those would be evidence of non-normality, a violation of that assumption. So here is a little way to look at this. First off, a normal distribution, just like we see in this top image, nice and bell-shaped, and you can see the points in the QQ plot are right on the line. The points that we have in our data set are consistent with what we would expect if they were normal. If we have a kurtotic distribution, in this case, it describes this kurtosis as the data peaked in the middle, but what we really pay attention to are the tails. If it's peaked in the middle, that means that the tails are going to be not appropriate. and we're going to have a different cutoff point than we normally would. And here you have sort of a version of that S shape, indicative of kurtosis. And then askew data, here we can see that we have a long tail, so we have a right skewed distribution here. And you can see that in this case, we have the kurtosis forming this kind of reverse C shape with the tails pulling away from the actual line. So after we examine the QQ plot, we will have a thought about the way we're going, but then we can actually calculate kurtosis. And so we'll first look at what we do, and then we'll look at the image. So kurtosis, again, is a statistic measuring the heaviness of the tail when compared to a normal distribution. The normal distribution in the right image is the blue one. So what we get in Excel is excess kurtosis. So tails that are really different from the normal bell shape of the distribution. And so kurtosis would be 0 would be just normal. So if there's no kurtosis, then you're going to get a score of 0, and that's what you want when you do this little test. You want scores that are closer to 0. And if you have a positive score, that means you have heavier tails or more outliers. And so you can see over on the right that we have this really peaked distribution, but what to really pay attention to is the tails. We have these longer, kind of heavier tails. So if we were going to draw the line for where 5% of the data scores are, it would be a little different. So in the normal distribution, it might be maybe right around here. And in this distribution, this red one that has this high level of kurtosis, we might be looking over a little bit further out. So we'd have a different cutoff point. And if we have a negative score, that means that we're having a flatter distribution. If we have something like this, we're still far away from 0. We're in the negative range. And we can see that in order to get 5% of the values, our cutoff point might be right around here, And if we have a really lot of kurtosis, like in this yellow uniform distribution, well, then you can imagine it would be hard to even find a cutoff point for 5% of the distribution because the tails are so fat in that square distribution. The rule of thumb when interpreting it is that if your kurtosis is less than 1, it's close to normal. If you get a score like that when you do the test, you should be okay. If your kurtosis score is between 1 and 2, you might want to be careful. You're going to want to watch the tails. There's a little bit of deviation from normality, but you can still be okay if other indicators are okay. And if your score is greater than or equal to 2, you're having substantially non-normal tails, and you'll need to do a different statistical test. Something like this one that's at 3 would be a pretty big problem. And even this one over here with the excess kurtosis at 1.2, you'd want to be pretty cautious about that. In Excel, the formula is just equals curt, and then you select your range of values, and you will get this statistic. You will notice that when you do the Shapiro-Wilk test, which we'll do in a minute, you'll see kurtosis scores in that app that are a little different from what you'll generate, and that's okay. It's just a slightly different way of running the calculation. It shouldn't be too far afield from what you had with your calculation in Excel. Our next test for normality is to calculate skew. We're pretty familiar with skew, and we know why it's a problem, but it does, when we get the score by doing this, it's going to tell us the symmetry of the distribution. And so once again, 0 is a good thing, perfectly symmetric. If you get a positive score, that means that the tail to the right, you have a longer right side. And if the negative, then you have a longer left skew. So the rule of thumb, if you have a skew figure of less than 0.5, it's okay. It's normal enough for your calculations, and that's analogous to this red one here. It's a bit skewed, but it's still normal enough to do your calculations. If you have a score 0.5 to 1, you have moderate skew. This can still be okay, but once again, you want to be aware of it. And if you have skew greater than or equal to 1, it really is too skewed for this analysis, and you're going to have to do a different analysis. And the formula for Excel is just equals skew and then the range of scores. The last thing that we're going to talk about is what we call the Shapiro-Wilk test. And we can't do this test in Excel, which is why I want you to test the other indicators first. So this is a test that combines this information to see if your sample of data really deviates from a normally distributed population. And it's actually a statistical test, so you'll get a p-value. And so if your probability of getting, in this particular case, you don't want to reject the null, you want to fail to reject the null because you don't want your data to be different from normal. What you'll get when you run this test outside of Excel is a test statistic named W, and it'll have a range of scores from 0 to 1. And once again, it's not done in Excel. You'll come to a different site that I'll show you in the demo. So how do we interpret it? So if your W is close to 1, and remember you get a statistical test, and if your statistical test is greater than 0.05, this is what you want. You're going to fail to reject the null, and that means that your data are not significantly different than normal. And this is a good result. So probability greater than 0.05, W close to 1. If your W score is less than 1, but your probability is still showing that it's not significant, that means that your sample is a little bit non-normal, but it's not statistically significant, so you're okay to go ahead, but you want to be cautious, and you might want to mention that. If you have a large N greater than 30, it's even more likely to be okay. If your W is noticeably less than 1 and the probability says it's significant, you have to reject the null. That just means you'll have to do something different. You've rejected the null, your data significantly deviate from what's normal, and so you'll have to do something called transform your data, which we aren't doing right now. You're going to do a non-parametric test, a test that allows for this kind of sample, or you're going to just write about the limitation, and that's the one that we're going to elect to do for your midterm project. And if the W is very low, which they give as an example of what very low is less than 0.9. So it's not really that low, when we think about it, but that's still considered a strong departure from normality, and you probably would have seen this in the QQ plot, and the assumption hasn't been met. So to summarize, there are some assumptions for the one sample t-test. First off, you have to have a continuous variable from an independent random sample, and you need a normal distribution without serious outliers. You'll be testing for normality by looking at the QQ plot, calculating kurtosis, calculating skew, and conducting the Shapiro-Wilk test.